Okay, this is the ideal gas law. The concept of the ideal gas law is that if you have, this happened to me a lot when I worked in the lab, you have a really, really small sample and you need to know what it is, but you don't have time or you don't have enough gas to figure out P1 and P2 or V1 and V2, etc. Then you can use this gas law. You just have to realize that it's based on a few facts that are not really facts. They're not really true, but they're 99.99% true, so it's okay. Things like the gas molecules have no volume. Well, they do, but it's so small that it's insignificant. The other assumption is that when they run into each other, they don't lose any energy. Again, they do, but not compared to the total amount of energy they have. Anyway, those are things you do not need to know to do the problem. So the big thing about this, everything is the same as what it was in all the other gas laws. We just have a new variable. The new variable is R. R depends on what units you put your pressure, volume, in, and T in. So it can change depending on what pressures you use. But if you always use the same pressure, then you only have to memorize one R. So I'm going to use this one. This is if the pressure's in ATM, the volume's in liters, the N is in moles, and the T is in Kelvin. So that is actually the label for R right here. That's the label for R. Now, if I change to kPAs, it's a different number. But as long as I stay in those units, I'm fine. That was a commercial to let my cat out of the room. Okay, so now let's go in and find out what we know. We know that we have 5.0 grams. Which part would that be? Well, the only thing I can go to from grams is moles, so we'll assume that's moles. And we'll come back to that. And then we have 256 mmHg. mmHg is a label for what? Pressure. It's all about having those labels memorized so that you can tell what things are. And then temperature, it tells us straight up that's 35. So volume is our X. Now, remember, our pressure has to be in ATM, so we're going to change that. To ATM, which means ATM goes on the top, mmHg goes on the bottom, and then you use standard. So standard pressure, 1 ATM, 760 mmHg. And that came out to 0.33. I don't want to worry about significant digits right now, so I'm just going to put a bunch. Remember, the rule is always keep at least one more than what you're going to need. So hopefully I don't need 6. And then I'm going to move in down here because I don't have room. But N needs changed from grams to moles. And the molar mass of, what is it? Neon. So 20.18. And that I got to be 0.24777. And then temperature has to be in kelvins. And that I got is 308. So now everything is in the units it's supposed to be in. So now we can set up the problem. So we have 0.33682 times x equals in 0.24777 times, and PV, now I forgot the equation, PV equals nRT. So R, it doesn't really matter what order you do it in, I was just trying to be consistent. 0.0821 times T is 308. Multiply everything together, divide by this number that's with the X, and you should get, let's see, how many significant digits? So remember, go back up to the typed part, 2, 2, and 3. So I want 2, so I get 19 liters. So this one involves making sure, and I chose one that had a lot of conversion to it so I could refresh your memory on it, but this one involves making sure that you're in the units that match the R label. So your pressures, you want to be in ATM. Volume, you want to be in liter. Temperature, you want to be in Kelvin, which we're used to. And N, you want to be in moles, which we're used to. Those are true for any gas law. You have to be in there. But for the other gas laws that we did, pressure and volume just had a match. Well, here now they have to be in these units. Otherwise, your R value will change. But if you're in those units, this will always be R. So when you go to fill in your let statements, if you do that like I do, R is always going to be 0.0821. So that is ideal.